I want to talk about Tracko today, which is an ad-hoc mobile 3D tracking system. I did this work with Christian Holz and Kasper Hornbk. So Tracko is a tracking system for mobile devices, and it allows multiple users to do cross-device interaction without any infrastructure. So the people here are exchanging photos across the devices, but these devices are standard devices. We did not do any modification. What Tracko solves is the increasing need for the mobile infrastructure. We are finding more and more applications span multiple devices. For example, like Apple Continuity on iOS, Samsung Flow on the Android phone, and Microsoft Continuum on Windows phone. They also enable the interaction between devices in the proximity. But how do these devices actually be aware of each other? Typically, this application uses the Bluetooth low energy to detect the presence of the surrounding devices. But if we want to have their actual location, this application cannot do this. So you need to set up a stationary 3D tracking system like OptiTrack or Kinect. Tracko now brings 3D tracking to the mobile devices. So Tracko is an ad hoc mobile device-to-device 3D tracking system. So we achieve a 3D accuracy, pre-tracking accuracy of 11 centimeters within 1 meter. So to achieve this, we fuse 3 types of signal on commodity device. The first is Bluetooth low energy, and the second is inaudible stereo sound, and the third is inertial motion sensor. Here is a quick demo about how can we use this for interaction. So Tracko informs the device where the remote device is, and then when it detects the pulling motion, I can transfer the image between the devices. So in the related work, people have used video, radio, and audio to track the devices in the 3D space. For example, touch projector uses the back camera to enable the interaction with the remote display. And orienteer determines the orientation of proximate mobile devices using their back camera. So for radio, group together like places the spatial radio nodes around the environment and then run a triangulation to infer the rough layout of different radio nodes. And similarly, they triangulated the device locations using additional Bluetooth nodes. For audio, Surface Link detects the sliding gesture on the table using inertial and acoustic sensing, and Beep Beep detects distances between the mobile devices by exchanging the audio signal back and forth. And the same authors also explore the feasibility of the phone-to-phone 3D localization with a static calibration and a static device mounting. So Tracko detects the distances based on between the mobile devices by exchanging the audio signal. And let me give you some background about how this works. So if we have 2 devices in the 3D space, and we want to know the distance between the devices, if we assume the speed of the sound is constant, so we can infer the distance by the time of the flight. While the idea seems very straightforward, there are one main issue is the clocks on the 2 devices are not synchronized. So we use one trick to solve this. The device A will place like a sound first, and then the device B would respond a sound. So we have 4 timestamps, and in theory we can get 2 distance if the devices are synchronized. But these devices are not synchronized, so we could not get any distance. And when we sum them up and reorder them, and all of a sudden these respective timestamps are on the same phone. So the synchronization offset will actually be canceled out by each other. So in this way, we get accurate round-trip distance without any cross-device synchronization. So I will go through like the 3 sensors we are using in the Tracko system. So let's start with Bluetooth. The good thing about Bluetooth low energy is it's really a robust signal. We use it as a fallback signal when the audio signal is not available. So Tracko uses the Bluetooth to detect the presence of the nearby devices. First, we get a sense about what's the device available nearby. But the bad thing is like when we look at the Bluetooth low energy like technology, it can only provide a very close distance estimation, like close, medium, and far. But Tracko can calculate the centimeter level distance between the devices through the Bluetooth low energy. And the way we did it is we get the accurate distance from the audio cue. So when Tracko is running, we build a lookup table that maps the Bluetooth signal strength to the precise distances. So basically, we calibrate the signal on the fly continuously. And later on, when a new signal comes, we use the lookup table to calculate the distance. So in this way, the Tracko increases the accuracy of like BLE-based distance estimation. So for the sound, I will start with a debug video demo. And in this video, I made the signal audible, so you can have like a rough idea what's going on. So first, both the left speaker and the right speaker on the left device emit a signal, and both the microphone on the two phones receive the signal. And then the right device repeats the scene to get the round trip distance. And finally, we calculate the 3D offset based on that process. And when we look at the process in a more detailed level, and the device calculated 2 timestamps from the audio processing. And then the local clock device also received 2 timestamps from the radio when the remote device receives the signal. So actually, we get 4 timestamps for the distance calculation, and we get like 4 distance because we have 2 speakers on each device. And based on this 4 distance, we are going to calculate the 3D offset. So here is the signal looks like. The frequency we are using is the inaudible frequency, so the original sound is totally inaudible. And there are 2 components in the chirp, in the signal. The first part is beacon. It announces the signal and helps us to determine the precise arrival time. And the second component is the encoding, is payload. We use the bi-orthogonal chirp to encode the information of the sender device. So for example, the sound, where the sound is from, which like left speaker or right speaker, or is from like which device. And we also have included the checksum to validate the signal detection. So to achieve 3D prediction, the distance accuracy is really important for us. So when the microphone can record 48K frames per second, so multiplies the speed of the sound. If we detect the signal at the wrong frame by 1 frame, and the offset will be by 0.5 centimeter. So this error will propagate to the 3D estimation. So we really need to keep it minimal. So to achieve an accurate detection, we first run a high-pass filter to filter out the ultrasound signal, and then we run a match filter to detect the signal. And these peaks actually are the possible arrival times. And while this peak has a positive peak and a negative peak, so we run a Hilbert transform and convert it to in the same scale. And then we differ, but even after this, we still got multiple peaks because of the multi-pass issue and also some echo noise. So picking the right peak is also very important. So we defer the decision making after our payload decoding. So if the decoder failed, we will reject this peak. So in the most case, after the decoding, we will only have 1 peak. So we have 2 timestamps from the local device's audio processing, and we also have 2 timestamps from the radio when the remote device acknowledges the signal reception. So each device will have 4 timestamps for each signal. And since each device has 2 speakers, 2 by 2, we have 4 round trip distance. And based on this 4 distance, Tracko uses a residue model to calculate the 3D offset from the distances. So from the IMU sensor on the phone, we know the relative orientation. And so we can imagine the phone solutions would be spread out in the 3D space. And based on this, and for each possible solution, we can calculate and estimate the distance. And then we compare the estimated distance with our observation from the audio signal. And then we use the gradient descent to determine the solution. And here is another demo about how the 3D prediction works. There is one arrow on each device, and the arrow is pointing to the other device. So when I move the device around, the arrow is updated to the right direction. So there is no any additional infrastructure or hardware modification involved. And in this demo, we also only use the audio. So we didn't incorporate the Bluetooth low energy, and we did not include an inertial motion sensor. So from that demo, you may find that the audio-based only method is not very responsive. So to help this situation, we integrate the temporary data reckoning, in which we use the gyro transforms the Tracko's local coordination system, and we use the accelerometer to detect some small movements. And in this demo video, there are 3 bubbles on the Seneca's phone, and it's corresponding to the 3 other nearby devices. And when Seneca rotates the phones vertically or around his body, and Tracko uses the gyro to transform the Tracko's local coordination system. And all these transforms are temporary to the tracking. So once we have a new observation from the audio or from Bluetooth, this adjustment will be reset. We run 2 evaluations to validate the design of Tracko. We first test, for the audio test, we test 3 different frequency range, 2 in the inaudible range and 1 in the joint audible range. In the audible range, we want to test audible range because all these speaker and microphone on the commodity device are designed for the audible spectrum. And we also test the different lengths of the beacons. And we test different distance range, close, medium, and far. So we use the OptiTrack to get the baseline, which is our ground truth data. And we use 11 camera to get a sub-millimeter accuracy. And we want to evaluate 3 problems, how well the audio recognition is, and how well the distance accuracy prediction is, and how well the 3D offset prediction is. So here is the distance accuracy result. And we can see all of the chip signal design have a distance accuracy under 5 centimeters. And the best case is the disjoint inaudible. It even have an average distance error in 2 centimeters. So based on this distance, we calculate the 3D offset. And in the close range, we have an error 6.5 centimeters in the 3D space. And in the median, we have 15 centimeters in the 3D space. And when we, here is the size of a mobile phone in the comparison. So even in the median range, the Tracko's 3D accuracy is still smaller than the size of phone. So our tracking is actually pretty accurate. And we also run an evaluation about our Bluetooth-based distance estimation. So we run our evaluation around a mounted device. We collect the data around the device in different planes. And the accuracy we get is much better than the default method, which can only provide close, median, and far. And we have an accuracy in 17 centimeters. And we compare our method with other 2 methods, like a popular BLE debugging app, which is a located beacon, and another a theoretical formula method. We can see our on-the-fly calibration can improve the performance by 11x. So in conclusion, Tracko is a mobile device-to-device 3D tracking. Tracko provides a mobile device-to-device 3D tracking, and it works ad hoc without any synchronization or pre-calibration. And the accuracy is suitable for the cross-device interaction. And the most important is it runs out-of-the-box commodity devices. And in the recent days, the stereo speakers actually becoming the trend for the new devices. And this is my search. I did the search yesterday. There are more than 1,000 type of phones in the market with the stereo speakers. But there are still some devices may not have the multiple audio units. For example, watch. Watch has only one microphone. But Tracko can still work for watch if we already have 2 Tracko devices in the environment. And we can view the 2 Tracko device as one logical bigger device with 4 speakers. And we can apply the same method and to calculate the solution. What makes me really excited is the new iPad. The latest iPad Pro has 4 speakers. So if we apply like Tracko on the iPad Pro, we are able to track the watch in the 3D space with only one iPad. And finally, Tracko scales with the number of the devices. Because of the sound interference, the performance of audio decreases when we have more devices. But the performance of Bluetooth low energy increases because we can now interpret 3D position based on Bluetooth. So the signal type Tracko use are actually complementary. And we can even integrate Tracko into the Bluetooth low energy based indoor tracking system and improve the tracking performance even more. And thanks, I'm happy to take any questions now.
So we have a few minutes for a question. Please get the mic. Someone will run the mic over to you. I'll kick it off with a quickie technical question of mine that I've always worried about with these RF-based systems. Does RSSI and Bluetooth depend on the orientation of the device, the orientation of the antenna with respect to the other devices?
Yes, it does. But what we did is we also have a dynamic updating lookup table. So basically, even if the orientation changes, we still have a new calibration coming. So the value is still up to date. But for the orientation, actually, my next talk will talk more details about what's the orientation's influence on the distance estimation.
Any questions from the audience?
Yes, very nice work. I was wondering, did you do an evaluation of the orientation accuracy as well? Because this is distance, right, that you reported?
Yes, and the sensor reading is very noisy. So in the past work, they propose a geometry method, which is based on the perfect mathematical calculation. And we find this method doesn't work because the orientation sensor is really noisy. It's not really noisy, but it's not very accurate. So that's why we use the residue model. It's kind of can tolerate some of noise, and this still works as you can see.
Yeah, but you don't have any suggestion as to what the deviation would be in terms of degrees or something like that of angle?
Yeah, we can use 2 types of the sensor data. The first is the orientation data. Yeah. And actually the orientation data is from the gyroscope is pretty clean. But the data from accelerometer is always have some drifting. Mm-hmm. And so that's why for data reckoning, we don't incorporate the data reckoning all the time. We only use it temporary. When we have another reading from the audio or from Bluetooth, we would reset all the data reckoning data.
Okay, thank you.
Any others? I was wondering, what's your sense of how well it works in a very noisy environment? Like if I'm standing in the middle of a park in a city center, maybe with lots and lots of Bluetooth devices around that aren't participating in your model and lots of audio noise. Is that something that
we did think about this, and actually the main challenge is not about how noisy the environment is. It's more about how good the CPU is, because the sound is very expensive. And if the CPU can improve in the future, and we can look at this more it's not so obvious peaks, and we can verify if this peak is the right peak, and then we can make it still work in the noisy environment. But currently, we mainly test it in a standard office room. So there is some people talking, but there is no huge noise in the environment.
What's your sense of how ready this is to go into a product? And if it's not completely ready, what are the main things that need to happen to make it ready for product?
Actually, we did a talk with like our folks in the production, like at Yahoo. And the main concern I got is they are afraid of the battery because processing the sound actually is pretty expensive. If we run the signal processing all the time, the battery will drain out very quickly. And this, I think, is the main concern. And another concern I have is about the performance of the microphone and the speaker. And they are really bad at the ultrasound like part. So we did lots of like the parameter tuning to make it work. But for making it generic on all the devices, I think it may need to improve the quality of the microphone and the speakers.